All right. So this is a subject on power electronics. So for electrical engineering students. So for this subject on power electronics, we have to follow this scheme. First of all, to tell you about the lectures. So we'll be having 2 lectures a week. And for this course on power electronics, the prerequisites that you need to fulfill are basic electronics. So the basic concepts of electronic circuits and basic concepts of electrical circuit theory and analysis you have to fulfill. And at the same time, you need to have the basic understanding of linear algebra, network theory, and some know-how about the electrical machines. And to follow this course, we have to use the following scheme. So there will be tutorials, and we'll be doing some tutorial examples once a week or once in 2 weeks. But basically, we'll try to do it once a week. So whatever theory we have covered, so we'll be doing some tutorial examples on that. Apart from tutorials, we also have lab sessions. So the lab sessions will mostly be MATLAB based or Simulink based. So some topologies or some circuits you have to design, and then you have to analyze, and at the same time you have to understand the waveforms. So these waveforms I will explain you in theory lectures or theory classes. And then you have to use your knowledge which you have gained in theory in lab practicals. We'll be having one minor exam, like kind of a midterm exam. So the details of the course or the details of the syllabus to be covered in exam will be given to you 1 week in advance. And then there will be a final exam at the end of the course. Minor exam will carry 30 marks. Final exam will carry 50 marks. Remaining 20 marks will have assignments and or quiz. So quiz will be kind of multiple choice questions. So you will be given multiple choice questions and you have to answer these for quiz. And for assignment, we'll be having some design examples. And about the schedule of this course or a lecture plan of this course. So we'll be covering the complete syllabus of this course on power electronics. And every week we'll be covering some part of it, starting from introduction of power electronics. And then we go forward with some basic understanding of circuit components, passive as well as active components, and then how to analyze these electronic circuits or power electronic circuits in terms of power, energy, and some other parameters such as efficiency and all. And then it's very important to understand that how to analyze these circuits using waveforms and what are the other performance metrics to analyze the power electronic circuits. So then we'll also be covering some of the power processor techniques or power converter topologies. So basically we'll be covering about 4 types of converter topologies. We'll start with AC to DC power converters, also called as rectifiers. So uncontrolled rectifiers containing diodes as switches, and controlled rectifiers containing the controllable switches such as thyristors. Next, we will be doing DC to DC power converters, also called choppers. And in these DC to DC converters, we'll be dealing with few topologies and step up, step down type of converters. Next, we'll do DC to AC converters, also known as inverters. And then at the end, we'll be doing AC to AC converters, also called cycloconverters. And then we'll be doing the examples or some applications. Before going into the applications, some basic understanding of control systems and how this control theory is applied in power electronics. We'll do that. And then 3 examples we'll be taking, or 3 application examples. Photovoltaic applications, motor drives, the drive applications, and then how these power electronic circuits are designed in low power chip design. And we'll take an example of the chip which normally used in mobile phones, mobile handsets, cellular handsets. Okay, so that was the lecture plan, and these are the books you need to follow. So Muhammad Rashid is one of the book that you can easily follow, and a part of this course will be following this book. And then the second book, Mohan and Len Robbins. The third book, Daniel W. Hart. So some part of the course will be following this book. And then Ericsson means Fundamentals of Power Electronics, and then Umanand. So maybe it's, I think, better to just refer all the books, and then you can decide which book is easy for you. But as far as the course is concerned, we'll follow the books on by this Muhammad Rashid and Daniel W. Hart. Now, we'll actually start this course now. So we'll first do the introduction of power electronics. So, and these are the 3 questions we need to answer. Why we go for power electronics? And once we get to know that why we go for power electronics, the next is that what is actually this power electronics and how to define, what are the definitions. And then once we know, including that the goal of power electronics or goals to be achieved by power electronics, will then go for applications which are actually available in the real world. So let's start this course now. So why power electronics? Because the thing is that we have to address some of the current issues related to this power system and power electronics. And we already know that these issues for power systems nowadays, because nowadays means for the last so many decades, we have a lot of dependency on fossil fuels, including coal, natural gas, oil, nuclear power. So these fuels we have a lot of dependency on for the last so many decades. And they cause environmental and health hazards. So we need to address these issues caused by the fossil fuels. So what to do then? Okay, so to deal with these issues caused by these fossil fuels, and we need to harness, or we need to tap on renewable energy. What is renewable energy then? Basically, we can just say that you already know that nowadays people are using this solar energy, wind energy, fuel cell energy, ocean energy, and so on. So these are a kind of renewable energy resources. So we need to tap on all these. We need to utilize these renewable energy resources. So why to do that? To get rid of all the hazardous issues caused by the fossil fuels. And we already know that the thermal plant, they cause a lot of pollution, environmental hazards. And ultimately, they have a toll on the health of human beings or health of living beings. And at the same time, they lead to carbon footprints, greenhouse gases, dangerous greenhouse gases, and then ultimately causing it to the global warming. And the radioactivity or the radioactive substance emitted by the nuclear power resources. So to get rid of all these issues, why not go for the renewable resources? And how to get benefit from renewable resources? Use the power electronics. So this is a link that we have to make, that why power electronics can become an important thing for normal day-to-day life, where we don't have, or where we have minimized environmental hazards and health hazards. So using renewable resources, which can help us in using power electronics, we can deal with the issues caused by fossil fuels. So we can reduce our dependency on these fuels. So that is the main or the basic requirement or basic reason for using power electronics. So now we know that, okay, using renewable resources which can help us in applying power electronics to a greater deal, which we'll study in this course. So are there any benefits if we use these power electronics? Yes, we can save the efficiency, save the electricity. In later slides, we'll see that. So about 15 to 20 or sometimes 30% of the power savings, means efficiency improvements, are possible using power electronics. These are the examples which we'll be covering in the later part of this topic. So normally we can say from 15 to 30% of the power savings are possible. So that's why I think we can say that we want to go for power electronics. This is just one example to prove what we are seeing in our previous slide. So this is the existing infrastructure for so many decades now. So turbines, like in thermal plants, the coals are burned, the coal is burned, and when the coal ash is burned, or sorry, the coal powder is burned, a lot of steam is generated. And then this, when this steam is generated, due to the pressure of this generated steam, the turbines are moved. And then this movement of the turbines will generate the electricity, because the turbine is then connected to the generator. So that energy is converted into electrical energy by the generator. And in this process, just in this process, we can say that 65% of the energy is already lost. So at the output of the generator, inside the thermal plant, we have already lost about 65% of the energy. So if we have renewable resources, then we can save on this efficiency at the generation part. We'll see later on. So just inside that plant, at the output of the generator, we have lost a huge amount of energy. So only 35% of the power is left, or energy is left, which is now sent to the step-up transformers so that it can be transmitted to long distances. And after this power is stepped up, then it is again connected to the step-down transformer, where it can be stepped down, like let's say to 440 volts. And during this process, stepping up and stepping down, we are losing some part of our power, means some efficiency is being lost. And then this 440 volts again step down to 220 or 230 volts, which normally we get at the households or some commercial places. So during this process also, some efficiency is lost, or efficiency becomes lower, so power is lost. And then this energy over here, or I am saying this power over here, after the step down transformer to at the output having 20 volts, we are just actually started using it, running pumps, running air conditioners, and all other household equipments. So we get about 16% here. So over this whole process, a huge amount of power has already been lost, causing revenue loss. So we know that during this process, we have lost a huge amount of power. So efficiency, if we can calculate, this is the output power, 16%, input power, let's say 100%. So a huge amount of power is lost. So the efficiency is, output is 16, input is 100. So very less. So it is about this one. This is, output is this one, the power input. Power input equal to, so the efficiency comes out to be 16%. 100, and at the output we have 16, so only 16% is remaining, so the efficiency is 16, which is very, very low. Normally we don't want that. So 84% of the power is already lost in this complete process. So to improve the performance of this complete power system, we need to improve the efficiency, which is the most important parameter in power electronics, or we can say power system. That's the main parameter in power system. So we know that high efficiency, if we go for such design in this whole process, if we change the design over here and improve on the efficiency and increase this output power, so we have already improved the efficiency then. So if we have done that, it means the losses are minimized in that case. So that's the whole idea. We want to do that. But at the same time, we want to have a smaller size of the equipments, reliable operation of all the equipments in the process. So that's what we want. And power electronics helps us to achieve this. We'll see later. So now we have seen that, okay, based on the current dependencies and based on the current issues, so power electronics we have seen that can play an important role in overcoming these issues. So now, what is the goal of this power electronics? To design an efficient power electronic system in order to supply high quality power. So high quality power means that it must have an high efficiency system. So power losses should be minimized. So if power losses are minimized, efficiency increases. And if efficiency increases, we have more at the output. So in that case, we can say that the quality of the power transmission system or power system is increased. So that's the main goal, to design an electronic system in such a way that we get a high quality power at the output, which is a load. And at the same time at a lower cost, which I have mentioned in previous slide. We'll see later on that how lower costs are possible. But at this moment, you have to understand this is the main goal. So winning in both directions. High efficiency at lower cost, high reliability. So how to achieve this goal? So we already know that nowadays state-of-the-art developments in electronics or advances in electronics have actually helped the engineers to make advancements in other fields by making use of electronics. So, such as semiconductor technologies at low cost. So, semiconductor technologies have already been advanced for last couple of decades, and now they are easily available for few decades already. They are easily available at lower cost. So we will use these advancement in semiconductor technologies at low cost. We can use this technology to achieve our goal. Next is, so this is possible. Next is efficient control algorithms. So already for the last so many years, people have been doing research and they have actually developed an efficient control algorithms, which we can run on computer systems or small integrated chips, and we can get efficient outputs. So we can make use of all these efficient control algorithms also to achieve this goal. And efficient signal processing algorithms. So signal processing and control algorithms can be used in one of the building blocks of power electronic system to achieve a high efficient power at the output. Means to minimize the losses in between. So if we use semiconductor efficient control and signal processing algorithms, they should not consume so much power and they should not indulge in losses or power losses. Then it means that we have already saved the efficiency and we have already achieved our goal. So these are possible. And the last one is computing power at lower cost. So to run these control algorithms and efficient signal processing algorithms, we need a good computing power. So if we have a good computing power, then we can easily run these complex algorithms and efficient algorithms at lower cost. And nowadays we already know that this computing power, high computing power, is already available at lower cost. So we can use all these state-of-the-art technologies in power electronic systems or in designing power electronic systems to achieve our goal, which is high quality power at the load at lower cost. So that will be a kind of a syllabus for our power electronic systems, that how to achieve this goal. Okay, so if we do this, if we use these state-of-the-art technologies in designing a power electronic systems for high efficiency power system, so it means we can minimize the environmental or health hazards because there is no pollution in electronic systems. If we are using all electronic systems in between, so it means we are actually minimizing the pollution. No dangerous gases, no greenhouse effects, no carbon footprint. So we are actually improving the efficiency at lower cost, and at the same time, we are actually saving the environment from dangerous emissions. So that is the goal of power electronics and the ways to achieve this goal. So now, once we already are familiar that, okay, what are the benefits of power electronics? Why it is required? So what is the need behind using power electronics? Now, after this, we now come to the definitions of power electronics. So power electronics is actually a combination of two terms. One is power, another one is electronics. Kind of contradictory to each other, because if you're talking about electronics, these are low power circuitries, and power deals with high power circuitries or high power systems. So we have to combine these two to achieve our goal. That will be covering in later part of our course, that how to achieve this high power capabilities just by using electronics. Okay, so before going into details of this, we just go into the definitions. So I'll be giving you about a few definitions of power electronics. So several people, they have defined power electronics in different manner. So there's no standard definition yet for power electronics, but I have picked up about 5 definitions. So I'll be giving you about 5 definitions over here. So first one, power conversion. This means power electronics is power conversion by processing electric power to expected voltage. To expected voltage, current, and or frequency with semiconductor devices. So we use semiconductor devices to process electric power, to get expected voltage at the output, expected current at the output, or expected frequency at the output. Means we know this frequency can be 50 hertz or it can be any value. So to get the expected frequency at the output. So we'll be having about, just to give you a quick reference on frequency. So one is a switching frequency, which we use actually in power electronic circuits. And another one is the line frequency, which is actually used in power transmission. In these power systems or power lines, we normally have 50 hertz of power signals. And there is another frequency value, which is, or a frequency term, which is a switching frequency, which is this one. So for power electronics, we normally use more than few kilohertz of, it's not always more than, it depends. So the range, I can give you a range. So few kilohertz to megahertz. So these power electronic circuits, they operate on few kilohertz to few megahertz of frequency. And this is called switching frequency. Now, high ratings. We'll be discussing in detail about these terminologies when we go into the details of power system or power electronic circuits. Okay, the next one is high ratings. If we are saying that, okay, we are dealing with electronic circuits for power systems, for application in power systems, these electronic circuits have to have a high rating for these devices, much more than 100 volts, sometimes like 1000 kilovolt is also possible. And at the same time, high values of currents also, few kiloamperes of currents. So a large value of kilovolts for voltage ratings and a large value of kiloamperes for current ratings for these power electronic circuits to be used in power systems. We'll be doing all this later on. This power electronic subject has already developed about 30-40 years ago, and for about 20 to 30 years, it has been a kind of a hot topic in research area. And a lot of people have a lot of interest in doing research in power electronics for the last 20 years or so. And in that case, we can say that we have already seen some of the advancements in power electronics, like microgrids and electric vehicles. I will talk about all these applications. So due to all these research interests, newer systems have already been developed for the last so many years. And that's why I think power electronics can be an interesting subject. Okay, now what is the scope of this power electronics in terms of power? From milliwatts to gigawatts. So milliwatts in the sense that if this power electronic circuit is being used in, let's say, integrated circuit, or like, for example, application mobile handsets. So milliwatts, we are talking about power rating of milliwatts. And if bigger grids and the power electronic circuits are being used in bigger grids, larger grids, we can talk about megawatts or gigawatts. Applications we'll be talking about in later slides. Now, again, next. Again, talking about the frequency, why we go for high frequency in power electronics. So I thought that I just give you an idea first that why we go for high values of switching frequencies in power electronics. Because these things we will be using in power converters or power processors. We already know about this equation. The power in inductor is, or first of all, energy in inductor is half Li square. We are already aware of this. Because of the rate of change of current in inductor is LDI by dt, and then we can say that energy stored in this inductor is half Li square. And if we multiply it with frequency, we get power. So if we multiply this energy stored in inductor with frequency, we get power. Now, if we are talking about this power in electronic circuits, so there are two variables. One is inductor. So this is one variable that we can change. It is on the designer to decide the value of inductor, and another parameter is frequency. It is also the responsibility of the designer to decide on the value of frequency. So these two variables are designer dependent. So for the same power rating of a system, of a power electronic system, either we increase inductance, then we need to decrease the frequency for the same power of a power electronic system. But if we increase the inductance value and we need to decrease the frequency, then this inductor value, if it is increased, we need a huge and bulky inductor, expensive inductor, costly, high weight, less efficient, and all this. So then go for the other option. Increase this frequency, switching frequency. For the same power rating, we can lower down the value of inductance. So by lowering down the value of inductance, this small inductor is required, very small inductor is possible, low cost, low weight, no distortion, no problems, and high efficiency, we'll see later on. So that is the reason, to minimize this inductor value, very small value, which can give us all the benefits, we need to increase the switching frequency. So sometimes kilohertz, several kilohertz to several megahertz. And same is applicable for the capacitance. So smaller values of inductor or smaller value of capacitances are possible in huge power systems. And in current situation, or in older or conventional power systems, we need bulky inductances and bulky capacitances, increasing the cost, increasing the distortion. Distortion in the sense that a lot of active and reactive powers got imbalanced. So we got a lot of imbalances in active and reactive power, so causing disturbances in power factor, thereby causing disturbances in losses. And if we make a smaller value of inductance and capacitance, as we have already seen in electronic circuits, where we only need small values of inductances and small values of capacitances, like microhenry and so. So small values, so we do not get so many disturbances or instability problems and all these things. So this power electronic circuit can actually help us in saving costs. Saving efficiency, we have seen, saving costs, but in details we will do when we go for power electronic circuits. You have to remember these terminologies or these concepts, because these concepts will be used when we will be dealing with the power electronic circuits. Okay, now second definition, because the first definition was dealing with voltage, current, and frequency. So that's why I discussed about the frequency, which you have to remember, because we will be using that in power electronic circuits. Now second definition, power electronics is study of power processing electronics, that is to process and control the flow of electric power by supplying voltages and currents in a form that is optimally suited for user loads. Same way of saying it, but here it is saying process and control the flow of electric power. So we'll see that how to do processing and control. So let's say this diode, if we have a diode over here, we process the signal. If we have a transistor in a circuit, we process as well as control the signal. And signal is the flow of electric power. So we can process and control both. Control means how much to process and how to process. What is the value of processing? Either increasing or decreasing, or how much increase or how much decrease. So that is possible by control signal. So the control is for flow of electrical power from input supply to the output user load, for which is optimally suited, means which is actually required at the user load, at the output, which is possible due to control. Okay, so these things we will do when we go for power electronic circuits, but these definitions you have to understand. Now the next definition, power electronic is about controlling electrical energy flow from source to load with the help of power electronic converter. Same thing, but the other way of saying it, the same thing. We have to control this flow of electrical energy by using power electronic converter or processor, means power electronic converter or processor. Same thing, but the other way of saying it. This is the definition adopted by Wikipedia. The technology associated with the efficient conversion, control and conditioning of electric power by static means from its available input form into the desired electrical output form. Again, the same thing, but the only addition over here is the static means. So efficient conversion is required. Efficient conversion means if we have input of AC, at the output we want DC, so we need a conversion. Efficient conversion means as low or as high efficiency as possible and lower losses. Again, control and conditioning, control and processing of electric power by static means. That's the main term over here. Static means no movable parts are allowed in this part. So movable parts are not allowed means we just use static means. So in this case, we are just using semiconductor switches. Just by using semiconductor devices, we can do the whole processing from input to the desired output. Input is normally not in our control, but output is in our control. So it is upon the designer or on the engineer that how to design an efficient conversion by static means to get a desired output. So static means, what are the benefits? If we are using semiconductor devices which are not moving, no friction losses, no wear and tear, so only static. So the losses are minimized if we use. So just by using these static switches or static devices, we can actually save upon a huge amount of power because we are saving upon huge amount of losses. So if these losses are minimized, so efficiency becomes more. So that is the whole syllabus of our power electronics subject, because we will be dealing only with static means in this syllabus or in this course of power electronics. Last definition. So power electronics encompasses the use of electronic components, the application of circuit theory. Yes, we apply circuit theory. We use electronic components like semiconductor devices or inductance or capacitance. Use circuit theory and design techniques. So we use circuit theory and design techniques and development of analytical tools towards efficient electronic conversion. So again, efficient electronic conversion. Control. So control is required to get the desired output, and conditioning of electrical power systems. So means like we need to process these electric power to get the efficient electronic conversion. Same thing, but way of saying is a little bit different. Okay, before going further, I just give you one concept which we have seen in few of the definitions over here, that what we mean when we are saying desired output. Available input means it is available to us. We do not have control on the input because it's given to us from renewable resources. So if we have a smaller solar panel, if we have a larger solar panel, so it's not in our hand. Or if the wind is blowing fast or if the wind is blowing slowly, so how much power is generated by this change in wind speed. So input is there, but output is dependent upon our design. So that's why it is called desired output. How to change that? So let's say this example where we have a fixed output, and in this example we have a variable output. So we can vary the output to achieve our desired output or to get our desired output. Here we cannot, only fixed value. So we have to, in this case, this is the input here, and this is the switch over here, semiconductor device. In this case, it is a diode. So let's say a semiconductor device. So this input is connected to the output load over here through this semiconductor device. So input is a sinusoidal wave, and in a positive half cycle, this diode is conducting or forward bias, we get the output, this one. In the negative half cycle, this diode is reverse bias, not conducting, so we do not get anything at the output, so 0. Same, half wave rectifier. So for this, we have another device. Now we have a controllable input, a third input, a controllable input. So by controlling this input, we can actually control the output. So this is again the same input signal, sinusoidal. This is the signal. It means from here to here, this device is not conducting. This device was conducting for the complete half cycle, this diode. But this diode with a controllable input over here, or a controllable terminal over here, third terminal, we can decide that when to turn this device on or when to make this device conducting. So let's say from 0 to alpha, this device was not conducting. It was off. This device was off. So we cannot get anything at the output because this is off. So at angle alpha, we have a trigger pulse over here. We will see later on. So we have a trigger pulse which turns on this device, and we get whatever at the input. This is now conducting because we have turned on this device at alpha. We have turned on this device. Now this is conducting. So whatever is at the input, we get at the output. So we start getting at the output like this. The part earlier to this, when it was not conducting, we do not get. So when we take average of this and this, they are different. So just by changing this alpha value, we can change the average value of the output. But this average value is fixed. This average value can change depending upon the value of alpha. So that is the very, very basic concept of power electronic circuits. Very simple. Okay, so now we have already understood that the goals of power electronics and the concepts of power electronics and the definitions. So now, based on these definitions, we can decide upon the basic building blocks of a power electronic system. Based on the definitions, we will develop the building blocks. So this is the building block of, block diagram of a power electronic systems. And based on this, based on the definitions, we have made a block diagram. And all the definitions that were talking about power processing and controlling. From source, means from the input to the output. So based on definitions, we have developed this block diagram. And in this block diagram, we have these building blocks. One is the input and output power. So this is input power at the voltage. Let's say this is a source. So source has some voltage and current. So we can get an input power. And the load can be resistance, inductance, or combination of RLC. Any load can be there. So it has some voltage and current. So we have an output power. So these are the building blocks of the power electronic system. Another building block is the power processor, based on the definitions we've seen earlier. So this is a power processor. It processes the input and give us the output. And what is inside this will be discussed in the power electronic circuits, converters. This is another building block, controller. It controls the values of inputs and give us the variable output. So like in the previous slide, we saw alpha. So it controls the angle alpha. Let's say, very simple, it controls the angle alpha, and based on the angle alpha, changes in angle alpha, we get a change in output at the load. So at this moment, it's better to relate to the definition of alpha to these building blocks or to this block diagram. Later on, we will be talking in detail and more complex terminologies in power electronic systems. Okay, so what is in power processor? Power processor can have one or more than one power converters. So either a single or multi-stage. So this power converter actually contains semiconductor devices and energy storing elements. So semiconductor devices for switching and storing elements, energy storing elements like inductance and capacitor. So if we change the switching, so the stored value in inductance and capacitor can be varied. If we increase the frequency of switching or decrease the frequency of switching, again the storage values in inductances and capacitances can be changed. So by changing these parameters, we can actually get a change at the output. Details later on in power converters. Resistive elements are normally avoided in power electronic circuits because resistive elements normally, they consume the power and they reduce efficiency. They just contribute in power losses. No useful work they do, only they contribute to power losses. That's why they reduce efficiency. So we avoid using resistive elements in power electronics because in power electronics, efficiency is the main parameter. Controller, it controls the switching timings and switching frequency of the power converters or power processor, just like alpha in the previous slide. This is one just simple diagram of this power converter, power processor. So let's say this is a power processor. Inside this power processor, we are showing two converters. It can be three, it can be even more than that, or it can be a single converter. So depending upon the application, we can use any number of converters inside a power processor. So one power processor can have one power converter, so they are same, or it can have multiple. So just remember this power processor terminology and power converter terminology. So this is just a kind of a detailed overview of a power electronic system, which we show, which you have seen in this slide. So this block diagram can be detailed something like this. So in the same block diagram, we have this, a power converter or a power processor. This power processor does not only have switches, but it has commutation networks also. Capacitors are also there because we last slide, basically we talked about switches and inductance and capacitance because these are the main components. So these are the main components, but at the same time, we also have some supporting components. So you have to remember main components are switches and L and C components. But apart from these main components, we also have supporting components, some like commutation networks. We'll talk about these commutation networks. Transient suppressors. We'll see what is transient and then how to suppress these. Switching aid networks, snubbers. We'll see that why we need snubbers. So these are all protective elements. So supporting elements are for protection or for controlling the switching on and switching on of the switches, to control the switching and to protect the switches. So these are the supporting components. And these power processor is being controlled by the controller over here. We already saw one building block in the previous slide. So this building block actually controls or sends control signals and receives some output. And based on this, it makes decisions that whether to increase the switching speed or increase the switching frequency or decrease the switching frequency. And then this controller can be software based. So if it is a software based, you make a program of this controller, put it in a microprocessor, and then execute it. Or it can be completely hardware, a digital hardware or analog hardware. So this controller, this building block of controller can be designed either software based or hardware based. And this power supply is required to supply power to all the blocks. And this is an input filter so that no input noise should be received at the power converter. And this is a fuse which protects this complete circuit from high currents and all this. And this is output filter so that no noise should be received at the output. It filters out the unwanted ripples or noise and all this. So this is a basic detailed overview of a power electronic system. Okay, before going further, I think it's better to also compare power electronics with signal processing. So in power electronics, we know that the main focus is on the efficiency because we want to have highest efficiency possible at low cost. But in signal processing, the focus is on the information processing and minimum loss of information. Here it was, the focus was the minimum loss of power, means minimum losses of like power in terms of heat or otherwise. Here, power is not that important. The important thing is that the loss of information should not be there. If you're talking on mobile phone, so that speech should not be lost. The content in that speech should not be lost. That is the important part. That's the main focus of signal processing. So that's, I think it's easily understandable that here we avoid or we try to avoid power losses so that efficiency becomes high. Here we avoid information loss so that the distortion becomes less. So whatever we have at the input, we get at the output without any distortion of the input signal. Semiconductor devices in power electronics are used as switches. In signal processing, they are not used as switches. They are normally used in the linear region. So, so switches means either on or off, either cutoff or saturation. But in signal processing, we are dealing with these devices, semiconductor devices, in the third region, in the linear region, as you have already studied in basic electronics. But still, I will be touching upon these things when I deal with the semiconductor devices in the next lecture. Okay. Then the power handled by power electronics ranges from few watts or milliwatts to several megawatts or gigawatts. But in signal processing, the power handled is milliwatts most of the time to few watts only, never going above that. And in power electronics, the signals are generally periodic in nature. And the signal in signal processing, we are normally dealing with aperiodic signals, like speech signals and all. Signal processing, just to give you a brief overview, that we can either work on analog signals. This is the input signal. Input signal can be input signal, or this is the information. It can be in analog form or digital form. Processed output information can be in analog form or digital form. Or if the input is in analog form and we want output in digital form, we need to convert through analog to digital converter and then process it so that we get a processed digital output. The same over here. If we have a digital input over here and we want analog signal at the output, we can convert from digital to analog and then process it and then sense it. So these are all possibilities in signal processing, analog or digital signal processing. But in power electronics, as we have seen in definitions, they were talking about power processing. This is power processing based on the definitions. This is input power. So it can be any value. It can be a DC, having any amplitude or any value, or it can be AC, having any value over here. And then this DC or AC signal is processed in the power processor, and we get a processed power signal at the output. It can be a changed DC input or DC signal, or a changed AC signal. Change in terms of the amplitude or frequency or phase. And what is inside this power processor? If we want to get from this input of DC to AC, we need to have a DC to AC converter inside this power processor. So DC to AC converter, or AC at the input, DC at the output, we need AC to DC converter in the power processor. Or input DC and output DC, varied DC output, we get DC to DC conversion in the power processor, or AC to AC conversion in the power processor. These are possibilities. So these are the actual power electronic circuits, also called power converters, we'll see. And this is the controller building block over here, which sends control information to the power processor, as we have already seen in the earlier block diagram. So now you can remember what is inside the power processor. Next slides, it will be even more clear. But these topics we will cover in detail in next sessions. So these are also called different modes of conversion. One is AC to DC, which is also called rectifier. So input is AC, output is DC. Another one is AC to AC. At input we have AC, at output we have a varied or changed AC, change in magnitude or frequency or phase. We call it a regulator, just like a fan regulator. Input DC, output DC, we call it chopper. DC to DC converter, we call it chopper. DC to AC, as we already know, we have inverters at home, so they convert DC to AC. So any value of AC we can get from this power converter, which is called inverter.